Okay, we've got our iPod Touch sales data here. Our data come from 2007 to 2012, quarter 3 2007 through quarter 2 2012. We've got our sales in raw terms here. This is 172,000 from memory, jumping up to 1.7 million in quarter 4 of 2007. As we saw in the graphs earlier, we get these jumps in quarter 4. As we looked at our data, it looked like it made the most sense to use the natural log of sales because it seems like our sales might increase by a fixed percentage in each quarter 4. And because we've got our time series data here and we'd like to be testing for autocorrelation, we're going to go ahead and use a new tool, Analyze Time Series Regression Analysis with Autoregressive Errors. We're going to choose log sales as our dependent variable. Quarter 2, 3, and 4 are explanatory variables. And we'll start with just a time trend as another explanatory variable. Just a straight line trend for time, which doesn't look like it should fit our data perfectly. One last thing in the statistics tab. We've already got the Durbin-Watson statistic selected. In fact, we can't unselect it in this time series analysis. But we'd like the p-value for the Durbin-Watson test, and for some reason it doesn't give that to us automatically. We'd like it, so we'll check it. Okay, let's hit run, see what we get. We're going to see a pretty good R-squared, 66%. Our output does look a little bit different here. We've actually got two sets of output, the ordinary least squares estimate and these Yule-Walker estimates down here. I prefer the ordinary least squares estimates. I'm most comfortable with those, so I'm going to stick up here. So we've got an R-squared of about 66%. This guy here, this is our Durbin-Watson test statistic. We've got a test statistic of 0.53. So we've got positive autocorrelation, and it's significant. Okay, so this isn't great. We'd like to be able to model the data rather than just relying on our autoregressive errors, which we can do, but it's not going to give us a great great model to predict from. So let's see if we can do better. Well, one way that we might do better is to model the time trend better than with a straight line. See, a straight line, a single time variable here, means that we can only model general increases or decreases in sales over time. And we saw with our data that the sales were increasing and then decreasing over time. So that strongly suggested to us that we ought to have a quadratic term. So let's do that. Modify task, add in time squared as a explanatory variable. Hit run. Let's see what happens to our R squared. It was 66%, now it's 93%. Great news. Looks like we've done good here. We've actually got rid of the significant autocorrelation. So things are looking great. Looks like we've got a very good looking model here. Time squared, very significant. And so it looks like we did really well to add time squared. If time squared is good, maybe time cubed is good. We could try that. Let's modify our task, add in time cubed. Time cubed goes in as an explanatory variable. Hit run. Our R squared was 93%, now it's 95.6. Okay, even better. Our Durbin-Watson test statistics still not significant, still no significant autocorrelation. And time cubed is again significant. Alright, if 3 are good, maybe 4 is good. So let's try adding in time fourth. Hit run. And our R squared barely went up. And time fourth is not significant. So we would say here that we don't need time fourth in our model. We'd modify our task, get rid of time fourth, and stick with the model with time squared times cubed as our explanatory variables, along with our 4 quarters. Once we're done modeling, now it's time for us to interpret. And we can say, okay, quarter 4 is significant. It's got a value of 0.9093. Since we've got log sales as our dependent variable, that means that quarter 4 sales are about 90%, 91% higher than quarter 1, 2, and 3 sales, because quarter 2 and 3 are not significantly different from quarter 1. So it looks like we just have extra sales in quarter 4 and about the same sales in quarter 1, 2, and 3. We could, in principle, interpret the time trend, but when we've got a polynomial, it becomes difficult to interpret and actually not that important in this case. We could use this model for prediction going forward if we wanted to, and we'd be reasonably confident in predicting for maybe the next 1 or 2 observations. But as we get further and further out from that, we'd get less and less confident predicting into the future, and I'll explain why in the very last section of our time series lesson.